Okay, good morning. All right, so I'm sorry, but I'm going to have to make you wait a little bit longer for the exam cutoffs. Like I said last week, we're still working on that, and we still need to get the numbers finalized. And there's one person holding out. And anyway, long story short, please wait a little bit longer for the cutoffs. Once I get them, hopefully today, I will email them to you. Okay? So just be patient with us for a little bit longer. And thank you. Okay, so today we're going to look at section 16.6. We'll be looking at parametric surfaces. So the idea of parametric surfaces is just like parametric curves. So let's look at that again. A parametric curve is R as a function of some parameter t, remember, and whose components are x of t, y of t, z of t, and t goes from some a to some b. So how this works, if you remember, is if we have our coordinate system sitting here, and from the origin, let's say that point is from R at T1, and we have some other point at R of T2, and some other point R of T3. Then we simply connect the dots, and we have our parametric curve that has some kind of direction as t goes from A to B. Okay, so that's the idea of parametric curve that we already have been using quite a bit. Now we're going to extend that to a surface. As opposed to just a curve, some kind of curve here, we're going to make that a surface. To extend that, remember, think about what's going on here. A curve can be thought of as a one projection of a surface. So to make this a surface, we're going to use two parameters. We're going to use two parameters to form a parametric surface. Now we're going to write it as R, still in the vector form. And we're going to use u and v as symbols for the new parameters. So just like with the parametric curve, we're still going to have three components, or three-dimensional, of course. And as usual, u can go from A to B, and v goes from, say, C to D. So the idea is very similar. Instead of one parameter to get a curve, now we use two parameters to get a surface. If you imagine you have some kind of surface, let's say this thing right here, then in order to form all the points on that surface, each pair of u and v is going to give you 1 point on that surface. And so on. Okay, so that's the basic idea of parametric surfaces. It's just like parametric curves. You use some kind of parameter and allow the parameter to run from A to B with a curve, and you accumulate the points. Same thing here. We extend it to one extra freedom here, two parameters, U and V. And then as U and V change, when they're allowed to change on the domains they have, we accumulate the points on that surface. So let's talk about the simplest surface that we can deal with, the plane. To form a plane, we need to know one point on that plane. And to form a plane, we also need two non-parallel vectors on that plane. To see how this works, there's our coordinate system. And let's say we have one point here. Let's call that x0, y0, z0. And the vector going from the origin to that, we'll call that r0, the vector r0. Okay. Now, suppose we know two vectors that's lying on that plane, two non-parallel vectors on that plane. I'll draw them this way. Let's see. Let's call this vector A, and we'll call this vector B. Then you can imagine this plane is formed by the vectors kind of like that. Okay, so that I use the dotted line to outline the part of that plane. So we got two planes. We got a plane here with one point that we know and two non-parallel vectors on that plane. Now notice to get all the points on this plane, I'll write down the equation here, and if you look at it, it actually makes a whole lot of sense. It's a surface now, so we need two parameters, u and v. This alone puts me at this point. If I want another point on this plane here, I need to add from that point some multiple of A and some multiple of B. So we're going to write it as U times A plus V times B. For example, this point right here, I can get that by starting here and then go this much to the right and then this much up. So this one here, this could be some U1 of A, and this one here could be some V1 of B. So U and V can control how long I'm going to go in the A direction and the B direction. If I want to go opposite to A and B, I use negative U and V. So there are numbers I control. So here I can go maybe say 3/4 of an A plus maybe 80% of a B to get me that point. And now by tweaking U and V again, I get another point somewhere on this plane. And I keep tweaking that, eventually I can accumulate the entire plane. Does that make sense? Okay, does that equation make sense now? Now you see how it works? Good? Okay. We can also write these in the scalar form. So suppose that the original point, the point that we know for certain is x0, y0, z0. And let's say A is made up of A1, A2, and A3, whatever they are. And B is equal to B1, B2, B3. Again, whatever those numbers are, they're just vectors. Then the scalar form of this equation would be the x component of that vector equation. So that would be x is equal to, the x component of that is x0, plus u times the x component of A, which is A1, and v times the x component of B, which is B1, sorry. And so on. Okay, so we can write it very neatly in the one compact vector equation, or you can split them up as 3 scalar equations for a 3-dimensional plane. Of course, this can be extended to higher dimensions, because all of the mathematics we've done here still carry over to higher dimensions. All right, let me show you a concrete example of a plane here. Okay, so we have equation written this way. We know it's a surface because we got 2 parameters, and the x component of that surface is 2u plus 3v, and then 1 plus 5u minus v for y, and 2 plus u plus v for z. If you had trouble recognizing these things, just like with other surfaces, break it down into the components and see what you can do with them. So let's look at the x component of this surface. The x component is 2u plus 3v, right? Now we're going to write this in the form on the last page, at the bottom of the page. Write it as x sub 0 plus u a1 plus v b1. So I'm going to write this as the number 0 plus u times 2 plus v times 3, just like in the same form that we saw on the last page. So this will be the x number of one point on that plane. This corresponds to A1 on the last page, and this corresponds to B1 on the last page. We'll do exactly the same thing we did with y and z components. So this is 1 plus parameter u times 5 plus parameter v times minus 1. So again, this point must be y sub 0, right? This number. That must be a2, and that must be b2. Now with z, you get the idea now. We don't need to do anything with z, so this is in the form of a plane. See last page. That contains the point 0, 1, 2, right? 0, 1, 2. And the vectors A is equal to 2, 5, 1. And the vector B is equal to 3, minus 1, 1. Does that make sense how I did that? Is it clear? Yes? Good. So the equivalent equation, we could also write this equation as the plane, equation of this plane R of uv as, looking at the form in the box on the last page. I'm going to take the point I know for certain, put it as a vector, and then u times a 2, 5, 1 plus v times b in a vector form. Okay, and if you add these together, you get this thing put into the IJK notation. Okay, make sense? Okay, let's do a couple more examples. Let's work on identifying a surface given by its parametric equation. Plane is pretty easy to remember if you know the form of the equation. Now with the other things, you're going to have to rely on your knowledge of the other shapes we have looked at. So let's figure out what we're looking at here. Here we have u cosine vi plus u sine vj and uk. Okay, now we'll figure out what this thing is. Now we're going to be, the fact that we have cosine and sine means we're dealing with some sort of circular, elliptical kind of thing. So in some perspective of this surface, there's going to be some kind of circle kind of thing involved. Let's figure out exactly what we're dealing with. Now the idea here is to look for some kind of relationship between x, y, and z. Because if we can find that relationship is the equation of the surface. Then you just have to identify what that is. For example, notice what happens when I add x squared and y squared. If I square x, I get u squared cosine squared v. If I square y, I get u squared sine squared v, which is the same as u squared times cosine squared plus sine squared, which turns into, of course, u squared, right? So if I add the square of x and if I add the square of y, I get u squared. But knowing that z is u, this tells me that this is also equal to z squared. So here's the relationship I wanted. Relationship between the three variables, or as many of them as you can get. X squared plus y squared plus is equal to z squared. Okay, now you got a relationship here. Now you have to rely on the knowledge you have about the surfaces that we started looking at the beginning of the semester. And you're going to have to identify this thing. All right, so what are we looking at here? What shape is this? It's a cone, right? It's actually a double cone, a cone that opens up and cone opens down. Right, because you can write this as z is equal to positive square root of x squared plus y squared. So that gives you the upper cone. And it can also be the negative square root. And that gives you the lower cone. So here we have our double cone. One part of that opens up, part of that opens down. So you see the cone equation, which it's not terribly difficult, and you can see the circling here. For each constant z, we have circle of radius something, right? So there's our circle, and the circle is showing up in the fact that we have sine and cosine involved. So compare this equation to this equation. This we have a better chance of recognizing with what you already know. This is a little bit difficult to see what's going on. So to identify a parametric surface, find the relationship between x, y, and z. Questions before we do a little bit more with this? We good with this? Okay. So let me bring that equation back again. If we hold u or v constant one at a time, we get what are called grid curves. And what they are, these are essentially traces. So think of grid curves as the parametric counterpart of traces, slices of that surface that we have done a lot with. So let's see what we're looking at here. Here we have x is equal to u cosine v, y is equal to u sine v, and z is equal to u. So here, let's let u be a constant. And we'll call that C. Then what we get here is we have a constant times cosine of v. Y is a constant times sine of v. And notice z is unaffected by the fact that we let u be a constant. Z is a constant, sorry. Yep, there we go. So c is a constant. Z is a constant c. Now these two together, all three of these together, tells us that x squared plus y squared is equal to z squared, which is equal to c squared. So this says that the grid curves with u equal to a constant are circles of radius c. So like I said, it's exactly the same as traces of that surface. If you slice at a constant z, we get a bunch of circles. Here in the parametric world, we call it a grid curve. It's just a circle of radius c, and gets bigger as c goes up and down. And let's say that v is a constant. We'll use d here just to use a different symbol. Then x is u times cosine of d, right? Which is u times some constant. I'm out of numbers. Let's use a here. Because d is a constant, so cosine of d is a constant. And to make it concise, I'm just going to call it a simple a, which is another constant. Same thing with y. If v is a constant, which is d, then this is equivalent to u times b, where b is some other constant. And notice that z is unaffected by the fact that we let v be a constant. Okay, so let's see. These three equations together says that x is equal to u times a, which is the same as z times a, where a is a constant. Y is u times b, which is the same as z times b, which is a constant, right? So we can see a bunch of different curves here. For example, y, if you look at these two equations, if you solve for z and sub into the other one, we get an equation that says y is equal to b over a times x. That's a line, right? It's a line. Because if you look at this cone from the side, when you take a slice, you see the outline that looks like a triangle, which is made out of a bunch of lines. Where's my cone? Okay, if you take a slice of the double cone, you see these lines. That's what this is telling you. It also tells us that z is equal to 1 over ax, or z is equal to 1 over by. What this is saying that from all of these different perspectives from the side of this cone, we see a bunch of lines. From side, cone looks like many lines. Whereas from the top down, taking slices of z, the cone looks like a bunch of circles. So we have a bunch of circles trapped in a bunch of lines, and that's our cone. Yep. Just remember that all of this is just a bunch of traces, just different way of looking at different perspective and different slices of that same shape that we have done quite a bit with. Questions? Okay, so the trick in identifying a parametric equation is to look for the relationship between x, y, and z. Now we're going to go the other way. Now we're going to parameterize a known shape. Okay, the idea here is to go the reverse direction. Go from a relationship of x, y, z, x squared plus y squared is equal to z squared, to the R of u and v world. We're going the other way. Let's start with a simple one. Let's deal with this one here. X squared plus y squared plus z squared is equal to 9. So we all know this is a sphere, radius 3. And I like to write it as in the form of a vector equation, R of u, v. In other words, if I'm going to put together this entire surface one point at a time, and I can control u and v, what equation do I use here to put the entire sphere together one point at a time? There are many ways to do this. I'll show you two ways to parameterize that one shape here. Because we're dealing with a sphere, it makes a lot of sense to consider using spherical coordinates. And a sphere in a spherical coordinate system is a very simple thing. The equation is simply rho is equal to 3, right? Radius of the sphere is equal to 3. And that represents a sphere of radius 3. Now remember the relationship between the Cartesian and spherical coordinates. X is the same as rho sine phi cosine theta. Y is rho sine phi sine theta. Z is rho cosine phi. So here, because we know rho is 3, so this can be simplified a little bit. 3 sine phi cosine theta, 3 sine phi sine theta, and 3 cosine phi. Now here's the key part here. Looking at these three equations, xyz gives me 1 point. Each triplet of xyz gives me 1 point. And each point depends on phi and theta. So we're going to let these be our parameters. u and v. Okay, think about what the parametric equation is doing. If you give me a pair of uv, I can give you 1 point on that sphere. We're doing exactly the same thing here. If you tell me what the phi angle is and what the theta angle is, I can give you 1 point on that sphere. You give me another phi theta pair, I give you another point. And if we keep doing that, eventually I can accumulate my entire sphere. And that's precisely what this equation is trying to do. So we're going to arbitrarily let u be phi and v be theta. And that's a completely arbitrary choice. I could let u be theta, let v be phi if I want, but it really doesn't matter. So this means x is 3 sine u cosine v, y is 3 sine u sine v, and z is 3 cosine u. And that means my vector equation, parametric surface for that sphere, can be written as xi plus yj plus zk, or x I plus yj plus 3 cosine u k, right? We also need to give the bounds of u and v. These are parameters. We often have complete control over them, but very often they have some kind of restrictions on them. So here u is phi. What are the bounds of phi in a standard spherical coordinate system? Phi is the up and down angle. Remember? 0 to pi, right? And v is theta. Theta is the in-plane on the xy plane, east-west kind of thing. And the bounds for that are 0 to 2 pi. Good. So there we go. This is the parametric representation of a sphere. Right? And if you look at this, if you look at it closely, this is really kind of cheating here, because what we did is change this to spherical and call phi something, call theta something. But that's precisely what we have been doing anyway when we accumulate the points on a sphere. We choose a phi, we choose a theta. So really, we've been doing parametric stuff when we deal with surfaces all this time. We just never really actually called it a parametric surface. Let's do another example with the same shape, another representation. So one thing to note is that the way you choose to parameterize a given shape is not unique. There are many, many different ways to parameterize the same shape. For example, I chose to parameterize using spherical. I could have done the same thing with cylindrical, right? So let's try that. Let's try parameterizing cylindrical. Remember, in cylindrical, x and y form the polar coordinate system. So x is r cosine theta, y is r sine theta, and this r is not the same as the radius of the sphere, right? This is just some slice of a sphere perpendicular to the z-axis. And in the cylindrical, z is remaining z. Z stays the Cartesian z. We also remember that x squared plus y squared is equal to r squared. So there's not much I can do with x and y. They are what they are. We don't know what r is. R is going to change as we change the level of z. Theta, of course, is going to change, right? But z can be rewritten as 9 square root of 9 minus r squared, right? In fact, because we want the entire sphere, we're going to do plus and minus. Plus gives us the upper sphere. Minus gives us the lower hemisphere. So once again, each point x, y, z depends on two parameters r and theta, which, if you remove the geometric meaning behind that, just call it u and v, well, those are our two parameters. I can control r, I can control theta. To form all the points on that sphere, each time you need to give me an r theta pair, then I can give you an x, y, z triplet, and that's one point on that sphere. And we can keep doing that until we get our sphere. So again, arbitrarily, we're going to let r be u and theta be v. This step here just went from a geometric thing to a purely algebraic equation. Now, what do we do? Why do we do that? You'll see that in the next couple of lessons what we can do with the parametric surface equation. Okay? But for now, let's just get used to this process. So the parametric equation can be written as r of uv equal to x. X is u cosine vi, y is u sine vj, and z, plus and minus, 9 minus r squared, k. That forms our sphere. Once again, we still need to give bounds on the parameters if they are present. U here represents r. So in this particular case, what are the bounds of r or u? 0, 2, 3. Good. So u, this is the cross section of that sphere, right? Each time you slice at a constant z, you get a circle that's no bigger than radius 3. But if you slice near the top, you get a very small circle. But if you slice at the equator, you get a circle of radius 3. So each slice will produce a circle of anywhere between radius 0 to radius 3. And v is our theta. Theta is standard polar stuff, 0 to 2 pi. Oh, here, instead of, yeah, that's right. So u squared, right? That's right. Thanks. Yeah, because at this step here, we remove the meaning of r now. So here, this is a purely algebraic equation. The fact that it represents some surface we know, well, that's great. But, we could have a surface here that we just simply don't recognize. We can have a surface that's in 4-dimensional space that we don't recognize. But we can still do a lot of stuff with that. We can find the surface area and all of that stuff that you will see in the next couple of lessons. But before you can do all that cool stuff, we got to get used to this process. Let's do one more. Let's try part of the ellipsoid. X squared plus 2y squared plus z squared equal to 1. That lies to the left of the xz plane. All right, so here, x squared plus 2y squared plus z squared. Sorry, I want the 3 here. Yoink. It doesn't matter. It's an ellipsoid, you get it. It's not a sphere anymore. It's like a football shape kind of thing. So let's see what this looks like. If I make y and z 0, then I get x squared is equal to 1. That tells me that the x-intercept are plus or minus 1. 1 minus 1. If I make x and z 0, then I have y squared is equal to 1 over 2. So the y-intercepts are plus or minus 1 over root 2 here and here. And similarly for z, the intersection are plus or minus 1 over root 3. We only care about left of the xz plane. So we just want the left half of this thing. So we're looking at this partial football shape. I can't draw that. Use your imagination. Hey, that's not bad, right? Yeah, that's not bad. It's half of a football shape thing, the left half. Okay, so again, you can parameterize this in just about any way you want. Here, the restriction is we want y to be less than or equal to 0 because we want the left half of that. So why don't we solve for y from this equation? And we get y is equal to negative radical 1/2 minus 3 over 2 z squared minus 1 over 2 x squared. And I choose the negative because I want the left half of the ellipsoid. And here we can stick with Cartesian. So arbitrarily, let's let u be x. Arbitrarily, let's let z be v. So the parameterization could simply be r of uv is equal to the x component is x, which is simply u, right? U. The y component is this thing, with x being u, z being v. So negative radical 1/2 minus 3 over 2 v squared minus 1/2 u squared. And then the z component is z, but z is v, right? So there we go. So there's our parameterization. And that's, of course, not the only way to parameterize that. You can change this to other coordinate system if you want. You could have solved for z instead of y. There are tons of different ways to do it. And that's kind of the flexible feature, nature of the parameterization. All right, that's it for today. See you Wednesday.